Okay. For anyone who hasn't met me, my name is Arvid, and I'm going to talk about the BitTorrent DHT. So first will be a little. Oh, yeah, there we go. DHT is short for distributed hash table, and it is like a hash table where the payload, that's the values that you store in your hash table, is divided up across many nodes on a network. And from the BitTorrent's client's point of view, the DHT is used primarily, and this is sort of the original purpose of the DHT, to ask this cloud of unknown nodes, who else is on this swarm? I'm downloading this torrent, I have this info hash, I want to connect to other peers that have this piece of content or are also interested in downloading it. And the DHT says, yeah, here are a bunch of IPs and port numbers that you can try to connect to. So this is sort of the high-level interaction with the DHT from the BitTorrent client's point of view. These are sort of the subjects or the topics that I'm going to try to cover. If I go too fast or if I sort of skim over something that's non-trivial, please feel free to stop me and ask questions. There's a risk that I will do that. So essentially, the main topics here, I will try to organize it from most high level to sort of most technical and most detailed and implementation, sort of down to implementation level. So the protocol is the high level kinds of messages that computers on this network say to each other. The topology is about how do they organize themselves in order to work. And the routing is how do you find the right place in this sort of swarm of or cloud of nodes. And then a little bit more towards implementation. How do you implement a routing table to have these routing properties? And the traversal algorithm is sort of the last, how an actual lookup in this DHT works and how it's implemented. So to start with the protocol, there are 4 fundamental messages, or RPCs as they're called, remote procedure calls. Each of these are sort of requests or queries, and they each have a responding response that you get back when you ask, send one of these to a node in the DHT. Ping is very simple. You just send it to someone, and if they're still there, they will send a response back saying, I'm still here. Announce peer is also very simple. You say, hey, I'm on this swarm, here's the info hash, and this is my port that I'm listening on, and it will just store that information, most likely, and then just say, okay, I stored this information. And then there's get peers and find nodes. They're sort of similar because they both actually are recursive, and they essentially do who else is on this, like for the get peers, who else is on this swarm? And you'll either get back peers that are on the swarm, or you'll get back other nodes saying, I don't know, but you can ask these guys, they might know. And find node is very similar. It's I'm just interested in nodes close to this node ID. Who can I ask? Give me some nodes that are closer to this that I might be able to ask again. So the division is essentially these are sort of one-off messages that you just get one back, and the other 2 are recursive. So they typically mean that you have to do these repeatedly in order to complete sort of your traversal. So as an example, for instance, I don't know, it's kind of faded here. This is us, this is the DHT. We don't know anything about the DHT yet. We send in a message saying get peers for X, and we get back a bunch of nodes. So what we do then is, okay, we take those nodes and we send the exact same message again to those nodes. So we send out 3 messages here, and we get nodes back. And this operation repeats. We get more nodes, we send out more get nodes, and eventually it terminates by us getting, instead of nodes, getting values, and values are peers that we can connect to. Right, that's sort of the high level how the protocol works. One clever thing about the protocol is that in all of these messages that we exchange, whenever you send a response, whenever you send a request, you always include your own node ID, which we'll get into in more details in a bit. But it essentially helps to maintain the structure. So everyone you ever talk to, you know about their location in this space. So you can learn about new nodes simply by hanging out and talking the protocol as usual. So there is also some maintenance. In fact, let's skip to the next slide. The sort of higher level algorithms that you build on top of these 4 main messages that you need to do are to bootstrap, which is essentially you start out without any nodes or without any peers. You need to build some kind of understanding of who else is on the DHT. So what you do is you run a find nodes on yourself. So you find nodes primarily that are close to yourself because the traversal will get closer and closer to you. Again, we'll get into that in more details. The refresh buckets is a maintenance thing. Maybe this slide is a little bit out of order, but refreshing buckets is essentially maintaining your understanding of who is on the DHT, specifically the ones that you know about, so that you can evict people that are no longer alive and introduce more new people that have joined the DHT. But you don't necessarily need to do that very often because all the other traffic that you actually do when you, like the normal get pairs and find nodes that you would do otherwise, you will actually be introduced to new nodes and you will learn about nodes that have gone down. And then maybe the most important is the announce, where you actually, that's the one where you say, I'm on this torrent, I'm interested in other peers on this torrent, and by the way, I'm also on it, so why don't you add me to this peer list so that when someone else asks, they will get me. I figured I should mention there's a bit of spoof protection. I guess we're getting into some details already. Since the entire protocol is based on UDP, which means that there's no verification built in that the other end has the address that they claim to have. So it's possible to send out these messages and forge your source address. So what we want to do is we want to verify somehow that before we add someone to a peer list and hand it out to potentially thousands of people, we want to know that they actually are behind. There's actually someone behind that IP, and that they're not putting some poor victim for a DDoS attack or something in this peer list. So essentially, whenever you get a peers request, you respond with a write token, which is typically a MAC or a sort of a verification, let's say a hash of the source IP, port, target info hash, and some kind of local secret. So then when this peer that you just responded to comes back and announce themselves, they have to include that same write token that you just sent them. And if they don't know the write token, that means that they didn't get your response, and that would be an indication of them probably forging their source IP address. So that's sort of just a little bit of friction. You get a 3-way sort of communication before you actually trust someone. I feel like I'm going a little bit too fast here. But anyway, so the next topic is the topology. So now we're going back up a little bit higher level. Essentially, the question is, when you make these recursive lookups to traverse the DHT nodes to get closer and closer to the thing that you're looking for, be it nodes or peers, how do you do that? How can you? How do you know that everyone that you ask will have a better and better understanding of people closer to the place that you're looking for? And essentially, the way you do this is with you come up with some topology of peers. So this is sort of what you have. The DHT is made up of all these peers randomly distributed, and every BitTorrent client that has DHT enabled, which most of them do, regardless of which BitTorrent swarm you're on or which torrent you're downloading, everyone belongs to the same DHT. So this is sort of a global network. So the first thing you do is you have everyone assign an address or a node ID. So that's what this illustrates. They all have a very long address that they just come up with randomly. And then you can sort of imagine that all of these, you can plot these on a one-dimensional space where you start at 0 and you start at FF, and so on, which is the largest number. So it would look something like this. Node IDs are 20 bytes or 160 bits, so that's start at 0 and you start at and you end at 2 to the power 160. Since everyone is randomly picking their own node ID, one property you have is that they will be uniformly distributed across this space. So this is sort of obviously a scaled version. There are millions of nodes. But essentially, the nodes will be located somewhat uniformly distributed across this space. One convenient property of using 160 bits or 20 bytes is that the node IDs have exactly the same size as an info hash. It's just a SHA-1 hash, which means that the node ID space is the same as the info hash space, which is not a coincidence. It essentially means that in this space, you put info hashes in the same space as the node IDs. So, for instance, if you have an info hash that sort of ends up here, you're extremely unlikely to have an info hash that actually coincides with the same node ID as another node. So it will end up somewhere in between some nodes. The nodes that are closest to this point in the space are responsible for storing information about it. So, for instance, these 4 would be responsible. So this is sort of where you're getting at, where you get when you're interested in this info hash. The goal is to find these nodes. So you want to find the nodes that are close to the whose node ID is close to the info hash value. Now, how do you do the routing? Obviously, it would be very impractical for every node to know about every other node. If you would do that, if everyone would know about all of the other millions of nodes, you could just go straight to the ones that are close to the info hash, and there wouldn't be any need for a recursive lookup. You just know it. The problem, though, is obviously there are millions of nodes, and nodes come and go constantly. So not only would you have to know about all the nodes in the entire world, you would have to update your understanding of all the nodes every time a single computer joins or leaves the network. So that the whole churn would be incredible. So instead of knowing about everything, you specialize in knowing about all nodes that are close to yourself. And the farther from you, the more sparse your knowledge is, or your understanding of the nodes that exist are. So, for instance, we can illustrate this as, let's say that we chose this node ID. So the distance from us is, that way and that way, and the further away from us, the less interested we are in them. So we could sort of map this into the distance from ourselves space. So we obviously are 0 from ourselves, right? And then we would just sort of, plot these nodes as how far away from us are they? Now this is sort of a conceptual illustration with using Euclidean distance. This isn't actually how it works, but it's a reasonable way of being introduced to it, I think. The main problem with this is, as you might notice, this whole space is empty. There are no nodes over here, obviously, because if we would end up in the middle, for instance, there will only be like the one half of this distance space would be entirely empty. So we don't have this nice property of nodes being uniformly distributed anymore from our point of view, unless we are in one of the extremes. You could say that with Euclidean distance, you sort of fold this space and you collapse it, and you know that this is the distance, right? And you collapse it into a single line, and that's sort of where you get the uneven distribution of nodes in that space, which is a problem. Instead, Kademlia, I guess I haven't actually introduced the name of this kind of DHT. It's called the Kademlia. The DHT uses an XOR distance metric, which can be a little bit unintuitive. It is, in fact, quite unintuitive. It turns out that it works well. So essentially what this means is that the distance between A and B is A XOR B. And the nice property here is that the distance metrics make everyone still uniformly distributed across this space. Let's sync that in a little bit. XOR, really weird.
Can you describe the XOR operator in case that everyone's familiar?
Right. So XOR is a bitwise operator where if you essentially if both values that you're XORing have a 1 in one location, or sorry, if they have the same value, you get a 0. If they have different values, you get a 1. So it's what's the
measure of how different the two bit streams are
yeah,
from each other.
that's a good way of describing it. Yeah, it indicates difference, right? If it's sort of like the not equal to operator, but applied on a bit by bit. Anyway, it turns out that the XOR distance metric still have all of the properties that you like in a distance metric. Like it has the triangle property, for instance, where if you have three nodes, they will, like, the distance between them will be consistent from all of three of them's perspective. Anyway, I have at least one more slide that might help with the intuition of how this actually works. So this is the distance space, distance from ourselves with the XOR metric. So nodes are still uniformly distributed. So what we do is we divide this up into this space into buckets, and each bucket holds no more than 8 nodes from our point of view. So this is sort of like how we simplify. Instead of knowing about every node, we only know about 8 nodes per bucket. And the way we divide these buckets up is that the first bucket covers half of the space. The second bucket, or bucket 0, covers half of the space. Bucket 1 covers a quarter of the space. Bucket 2, an eighth of the space, and so on. And it's not a coincidence that it's divided by half, quarter, and so on, because this essentially means that the first bit determines, like if the first bit is different from our first bit in our node ID, it means that it's on this half of the space. So then they end up in that bucket. If the first bit is the same, but the second bit is different from our node ID, they end up in this. So it makes it very easy when you look at node IDs in binary form, it makes it very easy to determine which bucket they end up in. And the key property of this division is that since each bucket can only hold 8 nodes, it means that for half of the space, you only know 8 nodes. And then for a quarter of the space, you know a different quarter of the space, you know another 8 nodes, another 8 nodes, and so on. So the number of nodes you know increases quite a bit the closer to the closer to yourself you get. So the half of the space is very sparse. You only know 8 nodes there, but closer to you, there's no limit really on how many nodes that are. The closer to you get, the more the amount of storage that you allow to know about nodes increases quite a lot. Okay, so this is also a little bit of a simplification, but I think it's very useful to sort of get the intuition for how this works. Essentially, what you do in a recursive lookup, you pick some nodes. Like, say, this is your target. You want to find an info hash or a node at this location, but you don't have enough nodes close to here. So you ask this guy. This guy says, "Oh, I have a pretty good understanding, not very good. This is the closest I know." Returns this node. You ask this node, which in turn returns another node, and so on. And for every step that you make in this, every hop, you will, on average, cut your distance to the target in half. So this is a binary search. The reason why you cut it in half is because of this division where buckets are divided in half, and when you ask someone with that's closer, their buckets will be differently divisioned than your own buckets, and they will have much finer granularity of nodes. So the complexity for this lookup is log n. And as I pointed out, the fine print, this is simplified. This would be the case if you had a Euclidean distance, but let's just say that it's distance with some notional distance. Okay, so let's look at the actual. This will actually be a little bit a deeper introduction to XOR, and how. Oh, is this the first routing table slide even? Yes, this is the first routing table slide. So this will sort of give an introduction to how you build the routing tables to hold these nodes and buckets, and also introduce a little bit how the XOR makes things very simple. So let's say, for instance, this is our node ID in binary form, and this is some other node's node ID, and we want to figure out which bucket it belongs to in our routing table. So what we do is we figure out how many bits, how long is our shared bit prefix. The XOR operation here actually would yield all these as zeros, because bits that are the same will be 0, and then this first bit would be 1, and then it doesn't really matter because we're just interested in the prefix. So since in this case we have 5 bits, it means that this node belongs in bucket 5. I don't know how intuitive this is, but it essentially means that if the first bit is different from our bit, it means that it's very far away from us. It's in the other half of the value space. So it ends up in bucket 0, because we have 0 shared bits. If we only have 1 shared bit, it means that it's a little bit closer to us, but still pretty far away, and so on. So the more shared bits we have in our prefixes, the closer to us it is, and the higher bucket number it is. And looking at the bucket division again, right, no prefix, bucket 0. Right, 1, 0. This is after you do the XOR, actually. Not entirely clear, unfortunately. When you do the XOR, you will have a number of leading zeros in the result, and that's the same as the length of the bit prefix. So if you have 1, 0 in your prefix, then it's bucket 1, 2 zeros, bucket 2, and so on. Now this is my slide where hopefully this will aid a little bit with sort of an intuition for how this actually ends up working out. This is not the distance space anymore. This is the node ID space. We are here. I put out the first 4 bits here in the value space. So if the first bit is 0, well, if all bits are 0, you end up over here somewhere. If all the four first bits are 1s, you end up over here somewhere. So if we are here, it means that our prefix to our node ID is 1001. The bucket 0 ends up being this, because it's a different first bit than ours. So this is done now. Now we're just concentrating on this. How do we divide this? Well, then we look at this second bit. The other half of the remaining space that has a different bit than ours is this. So this becomes bucket 1. And then we look at the second bit, which space has a different bit than us, which is this, so that's bucket 2. Then we look here. This is the remaining space now. The area that has a different bit from us is this, so this is becomes bucket 4, and so on. So this is sort of, instead of distance being just sort of the Euclidean distance away from us, we get first this, then this, then this, then this, and this. And closer to us, it might sort of go back and forth a little bit. That's the property of using the XOR distance. And it also conveniently fits in and makes it very easy to determine which bucket a node would belong to.
The maximum number of tries that you want to get from one node to another is 159, right? Worst case.
The maximum number of
hops that you have to go through.
Yes, if you have
Terrible.
if you have 2 to the power of 60 nodes in the world that belong to this,
Yeah.
which
Exactly, that's what
Yeah.
I'm saying. Okay.
yeah. So in the wild, there aren't that many nodes. There are. I would imagine that there's something. It's somewhere between 4 and 8 millions, or in that sort of order of nodes, which means that the longest prefix that you ever have with someone else is around 21 bits. So anything beyond that is just there for future expansion. So if we were to implement a routing table where we do this, right, we want 8 nodes here, 8 nodes there, 8 nodes there, and so on. The naive solution would be to just have an array of buckets where each bucket can hold 8 nodes, and we just create 160 of them. This is sort of inefficient because, as I just mentioned, the vast majority of these buckets would just be sitting there empty. The first 20 or so buckets would be used and would have nodes in them. All the rest would be empty. Another problem would be that if you have some random nodes that end up in sort of buckets very close to you, you really want them to be considered placed in the next sort of non-full bucket because when you're going to use it, you want to use them together. So this is kind of a naming solution. It works, but it's not very efficient. The way we do it in BitTorrent and most implementations, in fact, the paper sort of suggests doing it this way, is to start with only one bucket, bucket 0. You can add 8 nodes to this bucket. When you add the 9th node, so that it would overflow, you can't do that. So when you're about to add the 9th node, you split it. So you have bucket 0 and bucket 1. And then you move around the nodes that you already had in there to the correct bucket, and then you can insert the 9th node into one of them, maybe. If you're unlucky, you can't actually do that either, but for the most part you can. And also important, only the highest numbered bucket is ever split. You only split bucket 0 once. Once you split that and you try to insert more nodes into it, you just reject them because you already have a bucket 1. And then if you don't have a bucket 2, you can split bucket 1 and into 2 and so on. So to try to sort of illustrate this with a semi-animation is, let's say we have a bucket 0, we have 7 nodes, and we're just adding the 8th one. Great, we just added it. And now we have another node that we want to add. And we're like, what are we going to do? Well, let's first create bucket 1. So we split the bucket. Then rearrange the nodes, because some of these nodes actually would belong in bucket 1. And then add the node again. And then from this point, then you sort of just add nodes to whatever bucket they belong into. At this point, if you would try to add another node here, then you would have to reject it. Which is also sort of simplified. You actually keep sort of a cache of known nodes in case one of these seem to drop off. You sort of just replace it with a ninth node. That's advanced topic though. Okay, so let's switch into the traversal algorithm. This is I'm essentially going to illustrate how we do the get peers and announce peer queries. So this is where if you join a torrent, you have the info hash of the torrent. You want to ask the DHT who else is on this torrent, and by the way, also add me to this torrent. When you're downloading a magnet link, for instance, or any torrent, you do this regularly. Every 15 minutes or so, you sort of ask the DHT again and reintroduce yourself to the DHT to make sure that your entry in there stays alive. So the way you do this is first you pick nodes out of your routing table. You could pick all your nodes out of your routing table if you like. Picking a couple that you're fairly confident will be alive is enough. You sort them by distance to the target. The target is the info hash that you're looking up. And obviously we're still, distance now means XOR distance. So this is supposed to illustrate this sorted list of IP and node ID, and a little checkbox here for if you've already asked that peer. So the first thing you do is you send get peers in all directions for these 3 nodes. We typically want to limit the number of requests you have outstanding at any given time so that you don't sort of flood, and you might actually otherwise send too many packets and start dropping your own packets because of that. So we keep 3 or so requests outstanding at any given time. There are a few exceptions. If someone is taking a really long time to respond, we can assume that it's been timed out and start another one. But essentially, we keep 3 requests outstanding at any given time. When these come back, they obviously don't come back simultaneously. They come back out of order. So whenever one come back, we issue the next, and so on. For the purposes of this illustration, I'm going to pretend that they all come back at the same time with nodes. And we insert those nodes into this list in sorted order. Presumably, most of them will be closer to the target than ours because of their routing table. They will know more about close nodes than we do. So most of them will be inserted above these. But some might not be. So they might give us some nodes that are not necessarily better than any ones that we have. So now we have a bunch of new nodes. We want to keep 3 requests outstanding at any given time. So pick the 3 closest and request, send another request. And also mark off. Actually, I might forget. Yeah, so, right. If you already have the node, obviously we'll just sort of ignore it. And also, if a node doesn't respond, we want to mark it as stale. We don't want to remove it from here because then we might get it back and ask again. We want to remember that it's stale and that it doesn't work. So really, there should be another column here to say, oh, this node is broken. Don't ask it again. Right. And they're in sorted order. So we send out the 3 more requests for the top ones. And so on. We repeat this a couple of times. Typically, it ends up being maybe 20 times or so, sometimes less. And the termination condition is whenever we have 8 nodes at the top, and they've all been queried, and we have not, and they all worked, and we have not received any nodes that are closer, we can be fairly confident that these are in fact the closest nodes in the world or in the network. So once we have that, we know, okay, now we've found the closest nodes. They've probably given us a bunch of peers along the way. Now we send announce peers to all of them to say, okay, now you add me to your list. So when someone else asks, return me. That covers the traversal algorithm. That's all I had for my slide. I was going to put in some of the extensions we're working on, but I think that might be better for a separate presentation. Was that too fast? Any questions?
How do you find the piece of content? This is locating the peer.
Right.
Now, I know they're in the same space. So if you're looking for a piece of content with a certain info hash, technically, so I'm assuming the peers that are closer to that info hash would know about it, right? Is that the idea?
Right. So what happens here is when you announce, you add yourself to the peer list. So there's no content in the DHT. There's only peer lists. So when you know of an info hash, you can ask for peers on that info hash or on that torrent, on that swarm. And what you do is you tell these top 8 nodes about your existence on this swarm in the announced peer message. Which means that when someone else does a get peer and hits one of these nodes, they will get you back and they will be able to connect to you over BitTorrent. So yes.
So basically these nodes have no specialized knowledge about the info hash. They're just a statistical coincidence. So
Yeah, the info hash is just sort of...
The DHT ID, because they use the same...
Right, right, yeah. So the nodes don't know, really, they don't care what the info hash is or it means. It can be other things as well. Like it could be a hash of something else, for instance.
But the info
Yeah.
hash isn't stored anywhere in the DHT. It just happens to be close to the address of those things.
The info hash needs to be stored because, so in each of these nodes, they need to have a mini hash table to hold the portion of the distributed hash table that they are responsible for. When someone asks, when someone sends a get peers for a specific info hash, you don't get back just all of the pairs that they know of. You get back pairs that they know of have been announced to this specific info hash. So the info hashes are stored sort of in those nodes in that sense.
So like
Yes.
people who are seeding a particular info hash will announce themselves to the 8 closest people, and so that other people who want to find that info hash will also eventually end up contacting one of those 8 people.
Exactly.
Connected to the seed.
Right, right.
Gotcha.
Yep. So, right, as when you're downloading something or when you're seeding something, every 15 minutes you will do this, perform this operation where you search for new peers and announce yourself to the DHT. If you're a seeder or downloader, doesn't matter. The BitTorrent protocol is symmetric, so whether you're seeding or downloading, both will try to connect to each other at all times. So both parties would be interested in finding nodes or pairs and connect to those pairs.
What happens if you're only lucky enough that your DHT address coincides with the info hash in something like counting crows or something that we spam for?
Then you get a lot of traffic. We used to have a bug in our bootstrap router where we would hand out very unlucky pairs to millions of people.
Was it every 5 or 15 minutes we DDoS 8 people?
Yeah. So it's not that bad. If you can't cope with the bandwidth that you get, we actually throttle the DHT. So we will essentially start to appear to have gone down from everyone, and the DHT will sort of adjust and ask other peers to hold this information. But well, it wouldn't really help if the concern is that you waste a lot of bandwidth or use a lot of bandwidth. Having more than 8 would use even more bandwidth.
Makes DHT not very reliable. So I guess for a very popular concept.
So
Probably doesn't matter.
It seems to be generated pretty
So-
reliably.
You're not in desperate need of extra pairs if you're on a very big swarm.
well, the DHT will actually function very well because if a peer goes down or appears to go down, so in this case where it gets too much traffic, it will still respond to queries. It will just do it at no more than 4 kilobytes per second. So a bunch of people will still get responses from it. A bunch of other people will not, and they will store themselves in other nodes. So essentially what will happen is some people will sort of look like they're dead to some people, and you will sort of spread out. So you'll have much more than 8 in practice storing this information in that case. So which will have the effect of reducing load on the people that had too much load in the first place. So
Plus there's peer exchange, so once you find one
Right.
good peer, you can get more by asking that peer, hey, who do you know about? So there's other sources of information.
How long would it, in that situation, would it take the DHT to kind of like correct itself, or not correct itself, but to kind of spread the things out. So say there's like a huge jump in traffic on some counting crows thing that we put out in the world. And like, how long would it take from like these 8 people getting overloaded by it for it to kind of like spread itself out?
So everyone re-announces every 15 minutes. So essentially, everything would be reset every 15 minutes. But if you have a lot of peers, the problem is that the peers that announce themselves first, that then, like before these 8 nodes became overloaded, they might not be available for a while. But all of the subsequent nodes or peers that announce themselves will announce themselves to other nodes close by. And the more popular this piece of content is, the more peers there are, this sort of circle will grow. And one of the properties that you have when this happens is people doing this traversal of get peers, they will actually come across node or peers before they find the 8 closest nodes. So it's very resilient in that sense. And in fact, there are a lot of other problems on the internet that causes this to happen. Like there might be nodes that are visible to one set of the internet, but invisible to another set of the internet. Maybe you have a NAT or something that has some strange properties. So it's already the case that it's never as simple as it's the 8 closest nodes that store the information, because somewhere there will be bugs in clients, there will be quirks on the internet. You will end up with storing this information quite spread out.
So your announced peer could like kind of get lost if the receiver, their bucket that they decided you fit in was already full, then they would just kind of throw you out, or they would just ignore it, or?
Oh, sorry. So the announced peer stores data. It's the sort of store operation on the DHT. And if the message is not dropped and makes it all the way, it will be stored there. The bucket is just for the routing table. They might these guys that you talk to might not save your information or your IP in the routing table, but they will definitely save it in the sort of BitTorrent peer list, unless you exceed that limit too. Because obviously you can't save peers indefinitely. So there's much higher limit. I think we have. I actually don't remember. It's probably 1,000 or in the order of thousands for the limit on normal peers.
I have a question. Can we do anything fancy with bucket 0 once it fills up, like swapping nodes out to improve distribution? You know, swap good nodes to sort of improve distribution in that bucket or anything like that?
Nope. Okay. I don't think it matters necessarily. There are a few other tricks you can do to improve lookup times by prioritizing nodes with low latency, for instance. This is something that I'm hoping that we can implement soon. You can improve it quite significantly.
Any reason why 8 nodes in a bucket and not 17 or 4?
I don't think there's a very strong reason. My understanding is that the basic trade-offs that you make is we think that all of the 8 nodes will not go down within 15 minutes. That's essentially the assumption. If you put it in too many, you will waste bandwidth. If you put it in too few, they might go down and you will have gaps in availability. But essentially, so the original paper, I think, used 10. It's called K value, K buckets. K was 10 in the paper, and they used an hour, so they re-announced once every hour, and they used 10 nodes. I don't actually know why 8 was chosen and 15 minutes.
How often do we ping?
We don't necessarily ping just as part of the normal protocol. Typically, when you need to make sure that your routing table is fresh and that nodes are still alive, you do a find nodes in there too, so that you actually learn about potentially new nodes as well. And every now and then you do get nodes on yourself to learn about nodes that might be close to you that you haven't heard about. Yeah. Sorry, so actually, there's a funny anecdote. That we used the ping as a very clever mechanism back in the Windows XP days when you had a half-open TCP connection limit. We would waste a lot of time trying to connect to peers that were down. We actually used the DHT ping to first ping them. If they responded, we knew that they were up, and then we could sort of invest a whole TCP half-open by connecting to them, and that actually saved us, improved performance quite a bit.
Oh.
But now we use UTP, so we don't have this problem anymore. Anyway.
So, could you intentionally help or hurt a particular one by picking DHT IDs near it?
Yes, that is definitely a risk. You can launch different kinds of attacks by running whatever 100 nodes, and you pick nodes IDs that are very close to some target. You can gain a lot of control by doing that. I believe the Storm botnet was taken down by doing this, however, there's a paper where a guy actually tried to do this on the DHT, and he found that there's so much randomness in the protocol on the internet in different implementations that have different bugs, that it's very, very hard to actually shut something down entirely, because it's stored in so many places.
But what about boosting something that, like, say, that we're putting out that we know will be putting in traffic?
Oh, I see. To sort of alleviate some of the traffic on. Yeah, you could do that.
Host some of it ourselves.
Yeah.
You could have the router, in theory, do it, but we specifically made our router not participate in hosting.
Well, the router, I think he's talking about helping the hotspots in the DHT by running nodes in them. So if we know that we're going to create a hotspot, we could run some nodes. I don't think it's that big of a problem, typically.
Seems to work. Like,
Yeah.
we've had swarms with, 500,000, 1 million peers, and as far as we can tell, it's not perfect.
Yeah.
Let's see what our execution.
Patrick, do you have it? Do you?
So I'm curious how how like those 4 messages map to like the actual user experience, right? You start on a fresh BitTorrent machine, you add a magnet link, you download. I'm curious like what is happening.
So the first thing you do when you start up fresh and you don't have any nodes, so typically you actually save nodes between sessions. So when you shut down uTorrent, you save the nodes that you knew about last time, and you can try them to bootstrap from them. But let's say you just install uTorrent and you add a magnet link. First thing you need to do is to bootstrap. To bootstrap, you need to know at least one node. We run a router, so you ask our router, you get a few nodes back, and then from there you can go and primarily you do a lookup on your own ID to learn to sort of traverse the space closer and closer to yourself, so that you learn about all those nodes, and you populate your routing table that way.
And that's the part where there's the 0 bucket splitting.
Right, exactly. And then you do this get pairs traversal on the info hash of the magnet link that you just added. And then you announce yourself. Once you have pairs, you connect to them, and the first thing you do then is to download the .torrent file or the metadata from the swarm, and then it's normal BitTorrent from there.
So, but when you first bootstrap, when you get back a node, you put it in the bucket 0 automatically, whether or not is in theory could be in bucket 5.
Yes. The reason for that is because whenever you're going to use it, you want you could do that if you have the naive implementation of just 160 buckets. You just put them wherever they sort of would belong. But the problem is that as soon as you want to use them, you would have to go and sort of find them again, because you want to use 8 of them at a time typically. You want to respond with 8 of them at a time. And if they're spread out, you have to do a little bit more work to collect them.
One of the nice things is you can bootstrap yourself if you have peers through another source. So if for whatever reason the router is down and you have a torrent that has a tracker, you can go out and find peers to the tracker and then bootstrap yourself into the DHT network that way.
Right. Yeah. Whenever you connect to an actual BitTorrent client, you also try to ping it with a DHT ping to see if it's on the DHT, and if it is, you add it to your routing table.
I got 2 more questions.
Okay.
So both the get peers and the announce peers do the thing described on the bouncy ball slide?
Not the announce peer. At this point, you know specific peers. You know the nodes. You know the ones that are closest.
Well,
and you
from the get peers.
right. Right. So this is the sort of leftover state from the get pairs. Right. When you want to store things in the DHT, it's always coupled with first the lookup and then the store.
And the other question, maybe covered by the randomness bit, is what is the probability that the 8 final pairs that you actually arrive on are the actual 8 closest? Like, does it matter like where you started in the DHT?
It does not matter where you start in the DHT. The things that might get in your way would be nodes that are down. But you have so many routes to get to the 8 closest, so you're pretty likely to get to the actual 8 closest, unless like the entire network is split up into islands. That's not very likely to happen since there are so many sources.
How would that happen?
Well, our router would have to be down, for instance, and then you would have to have communities that don't ever talk to each other on the same torrents ever, for instance. I don't know. Or you could have net splits where you can't. Yeah.
What's the query response time? Does it generally happen? What can be done to optimize it?
That's a great question. It is much longer than it should be right now. No, it's much better than that, actually. Right. I think, don't quote me on this, I don't have any recent, like, any actual measurements, but I think each of these, can go back maybe, each of these get pairs. Oh, no. Oh. LibreOffice has like 1 second latency on switching slide. Okay. Each one of these requests and responses, right now, I think, come back in about half a second. So when you need 20 of those, it turns into about 10 seconds. So it's there's a paper with a bunch of optimizations to make this actually several times faster, which I'm hoping to implement soon. The thing you do is in your routing table you can prioritize low latency pairs so that you're more likely to ask people that are quick to respond to you. Other things is to try to make, like, you can make bucket 0 and bucket 1, for instance, much larger and fit much more than 8 nodes. That way you have a slightly better chance of getting closer. Like, you can skip a few hops in your traversal that way, and without it being too expensive. Oh, could do that. It would sort of defeat the purpose a little bit, I think. But yeah, yeah.
Can you send out a link to the original paper and then the optimization you're talking about?
Sure.
I'd like to read them.
Sure.
Awesome.
I guess I'll send it to TechNoise. Okay. Okay, sure. Is this the last question? Do I have it cut?
I don't recall the closer to target what that means. Is that like the time it takes to get a response back, or is it some physical distance?
Close to target essentially means a longer shared bit prefix in your nodes. That's sort of the simplified way of describing what XOR does. So if
I didn't understand, like, does that have any kind of physical translation? Like,
oh, you mean like actually where the computer lives in the world? You mean physically?
yeah, like I kind of forgot, like maybe it was in the beginning slide, but what is this gameness that, like, I don't even recall what the status code is.
So the node ID is entirely orthogonal or unrelated to where you live in the world. It's just a random number that you come up with whenever you start your BitTorrent client.
So I guess my question is, like, why are we doing this in the first place?
Right. So the reason why we do this is so that you can. Is this going to be 1 second per slide, really? Okay, well, now it's stuck. So that you can join a swarm even without a tracker. That's essentially the fundamental idea is to be able to do this. To ask who else is on this swarm and get a pair list back.
Okay, and the distributed is because we want to have it evenly distributed? Is that why we're doing this?
So you don't have any centralized.
Yeah.
So-
Some people shut it down this off by shutting down the trackers.
Right. So the when this was first introduced, it was somewhat common, and I guess it still is, that large trackers are not very reliable. They might be down for a day or so at a time, and this and what you're suggesting is a centralized solution, which is the tracker, which was the sort of original and still most reliable way of doing this, of connecting pairs to each other or making pairs find each other. This is sort of the fallback. If you don't have a tracker, or if the tracker is down, you can always rely on this, because this is much more reliable in the sense that internet can break in some ways, but as long as it's not totally broken, you will still be able to use this.
I guess I was not, I didn't know if the way that this is done, so it doesn't take into account really anything about bandwidth or your actual, you're not getting those 8 nodes that are that will give you the best bandwidth. It's more of just you're checking.
You're not downloading any content over this from the DHT. You only get IPs and ports for pairs that you can then connect to over BitTorrent.
This is simply a discovery mechanism, not necessarily a content.
Right. It replaces the BitTorrent tracker, where you can say, I'm on this swarm, give me some pairs that I can connect to. So the nodes that you get, you don't need much bandwidth from them. You just need a small list of pairs. That's all you need. So, but also, to your question, no, there's no attempt at making those have specifically good bandwidth. It is all distributed, so everyone will participate in it. So everyone will be part of those 8 nodes for some info somewhere.
So this trackerless solution, has this been implemented on other clients besides BitTorrent and UTorrent?
Yes, essentially every BitTorrent client that
Like an open
matters.
standard that everybody uses.
Yeah.
You just brought up something interesting. Isn't the beginning part of the node ID, isn't that actually encoded from the IP address?
Yeah, that's sort of the advanced topic.
Well, doesn't that cause an issue if you have a major router outage? I remember back in the 90s, it was not uncommon for someone to bring back a major router.
No, it's not, because it's not the actual IP address. It's a hash of the IP address, so it will be uniformly distributed still.
Awesome. Okay. Yeah.
Okay. Okay.
Sorry. Okay. So you have your info hash and you're going to you're asking, well, basically, where are you asking to get these nodes from? There's.
The nodes that you already know of.
Yeah, but when you first get your info hash.
Right.
Where are you, you have to start somewhere to be able
Right.
to get that initial set of nodes
Right.
back.
So if you start up, so there are a few different places where you can find nodes to sort of bootstrap off of.
Yeah.
If you have any other torrents, for instance, you use all of those pairs as potential DHT nodes. If you have run uTorrent or your BitTorrent client previously, you might load some back from disk that you knew about last time. But if you don't have any of those, if you just install it fresh, you will also be able to go to our router.utorrent.com and get nodes to bootstrap from.
And are there other routers besides ours?
Not that I know of. I believe BitComet or BitSpirit might have been running one at some time. Maybe they still do. I don't know.
Fuse has one, but just for their own DHT.
All right, that's actually different.
I heard that transmission supposedly set one up, actually.
Okay.